And I'm back from a very hot shower. The rest of this lesson is about compound inequalities. Because if you're using inequalities in a real life situation, typically you're in a place where you have to make a decision, and that decision is subject to several constraints. Like total cost has to be under 1,000, number of moving parts has to be under 20, number of units produced has to be over 50, constraints like that. So we're going to talk about how to combine multiple constraints into one working system. And the two main ways we do that are the words and or. So let's talk about the difference here. If I say x minus 2 has to be greater than or equal to 5, or half of x has to be bigger than 6, then I'm saying I'm happy if you satisfy either one of these conditions. Doesn't have to be both, but one of them has to be true. So I would solve each of these separately first. Over on the left, I just add 7. X can be no bigger than 7. Oh, this shouldn't say 1 over 2. It should say 1 over 2x on the right here. Sorry. On the right, I just multiply both sides by 2. Since that's not a negative number, I don't have to flip anything. I just multiply both sides by 2. So x is bigger than 12. And the key word here is or. X is no bigger than 7, or x is bigger than 12. So the way that looks on a number line is here's 7, here's 12. X can be no bigger than 7, or x can be strictly larger than 12. So both of these intervals are solutions. Now here's how we write a solution set with more than one interval in it. We're going to write each interval separately. So practice along with me. You might want to pause the video here and see if you can get them on your own. Otherwise, we always go from left to right. So we'll do negative infinity up to 7. And then we'll do 12 up to infinity. So 7 gets a bracket, 12 gets a parenthesis, because this is a dot and this is a circle. The infinities always get parentheses. Then the way we glue these together is with a union symbol. It's just a big fat U. And this says my solution set is all of these and all of these. So the solution can be in this interval or it can be in this interval. Two different ways to think of it. But that's what the union does, is it just glues two intervals together and says, I'm interested in this whole shaded in set, not just one half or the other. So or means either one is fine. Let's do and now. Maybe my situation is negative 1/4 of t has to be strictly bigger than negative 2. And also, positive 1/2 of t has to be greater than or equal to positive 2. So these are my two conditions, and I need to satisfy these both to have a working system. I would solve each one separately. On the left side, I'm going to multiply by negative 4, because that's going to get rid of the negative 1/4, right? And that means I have to flip the sign. So on this side, I get t. On this side, I get negative 2 times negative 4 is positive 8. And then the sign flips, like so. Over on the right here, I only have to multiply by 2. So I get t is bigger than or equal to 4. And the sign doesn't flip, because I multiplied by a positive number. Let me draw two number lines here. Here's the first condition. Here's 8, and t can be anything less than 8. Here's the second condition. This is 4, and t can be 4 or anything bigger. So our solution, we have to satisfy both. This is an and situation. We have to satisfy both, and that means if it's less than 8 and bigger than 4, it works. But if it's only one or the other, it doesn't work. So none of these numbers work, because they're less than 8, sure, but they're not at least as big as 4. The first number that works is 4. It's in both shaded areas. And then 4.5, 5, 6, 7, 7.9, 7.999, those all work. But 8 doesn't work. 8 is bigger than 4, but it's not less than or equal to 8. So 8 is the first number that doesn't work, and any number 8 or bigger is only on the bottom line, not on the top line. So these are the only numbers that fit both this condition and this condition. They're in both shaded areas. And so we can write our solution as the interval 4 with a bracket to 8 with a parenthesis. Do you see? Okay. Let me show you a 3-part inequality. I could write, if I know that my expression has to be in between two values, let's say I know I have negative 2x plus 7, and I know it has to be in between 5 and 11. Let's say bigger than 5, no bigger than 11. Rather than write two inequalities and say, both this one and that one have to be true, I could write it like this. It has to be bigger than 5, and it has to be less than or equal to 11. So this is a way to write those two inequalities as just one 3-part inequality, and it comes with its own special fun algebra rules. This is like an equation, and it's like an inequality, except instead of having 2 sides, it has 3 sides. It has a left, a middle, and a right. And the way this works is I can manipulate this, but whatever I do to one side, I have to do to all 3. So when you're keeping the balance, imagine you have 3 different platforms in your scale instead of 2, and we have to keep the balance for all of those. So I'm trying to get x by itself. I want to subtract this 7. If I do that, 2x plus 7 was less than or equal to 11. So now 2x has to be, or negative 2x has to be less than or equal to 4. And it was bigger than 5, so the new thing has to be bigger than negative 2. I have to subtract 7 from all 3 sides. Can't just do 2 sides, have to keep the balance. Whoops, that should be a positive 4. 11 minus 7 is positive 4. So I get this expression. Negative 2x is, whoops, I made a second mistake. There we go. Oh, no, don't want that. There. Get rid of that equals bar because there wasn't an equals bar before. You're never going to add an equals bar where there wasn't one previously, or vice versa. That never happens. So what I have here is now I have negative 2x, and I'm still trying to get that by itself. So I want to divide all 3 sides by negative 2. Okay. I want to divide all 3 sides by negative 2. So this first number, negative 2 over negative 2, is going to be 1. Negative 2x over negative 2, that was the whole point, is getting x by itself. And the third one is negative 2. Now the thing is, since I multiplied or divided by a negative number, the signs flip. Both of them. So this becomes this, and that becomes that. And that's our solution set. X is at least as big as negative 2, no bigger than 1. And you can check that. For example, negative 1 works up here. That'd say 9 is between 5 and 11. So negative 1 works. 0 works. 7 is between 5 and 11. But negative 3 doesn't work. That would make this a 13, and that's too big. 2 doesn't work. That would make this a 3, and that's too small. So it has to be between these two. The signs flipped. So for our solution set, I could write it has to be at least as big as negative 2, so that gets a bracket. And it can't be any bigger than 1, so that gets a parenthesis. I get brackets from equals bars. I get parentheses from strict inequalities. So that's how we handle a 3-part inequality. It's not so bad, is it? Let's do one more just to be sure. Let's say I had 10 is less than or equal to 5x plus 2. Actually, let's make that a 5x plus 10. This will be interesting. And that's less than, how about 20? Now, we want to be careful here. When I subtract 10, that goes away from all three sides. And that means the left side is 0, this is 5x, and this is 10. A lot of people's first instinct here is when they subtract 10, they think, okay, that makes the left side go away. It makes the numerical value go away, it leaves it at 0, but we still have 0 as a lower bound for 5x. 5x still has to be bigger than 0. It's not like subtracting the 10 removes the lower restriction on x. There's still a lower restriction, it's just expressed with this 0 right now. So be very careful with those. Similarly, up here, if I subtracted 5 from all three sides, it would say 0 is less than negative 2x plus 2 is less than or equal to 6. Subtracting 5 isn't a get out of jail free card that leaves you with just a regular inequality. You still have a triple inequality no matter what you add or subtract. So your goal, as always, is to isolate the x. So down here, I've started isolating the x by subtracting its plus 10 term away. And I'm going to finish the job by dividing by that factor of 5. So I'll divide all three sides, but come on. Now apparently when I tap, this is the worst. I have no idea why this menu keeps coming up. I wasn't even touching the screen that time. I just breathed on it. Am I allowed to breathe on it? Oh my God. Okay. The iPad is being very rude today. So, you have got to be kidding me. Okay. I'm going to divide all three sides by 5. 0 over 5 is 0. I don't have to flip the signs because this is a positive number. And 10 over 5 is 2. So my solution set is... Would you please behave? Maybe if I put this over here, it'll understand. So my solution set is anything bigger than 0 or equal to, but it can't be as big as 2, like this. All right, so that's 3-part inequalities. And I really only showed you those so that I could show you these. The next thing we're going to do is look at absolute value inequalities. That's the real end goal of this section. And the end goal of, well, I guess the end goal of chapter 2. But chapter 2 is really a catch-all chapter for techniques we didn't have anywhere else to put. Once we start chapter 3, the rest of the class is going to be kind of one unified narrative. This is the last splinter off of the main timeline for the course. So if I say something like this, the absolute value of x is less than 3. Remember I told you that absolute value represents distance. So a way we could write that out is, this is the distance from 0 to x, and this is a less than. So we could say x is less than 3 units away from 0. That would be how we'd think of this absolute value as a distance. So on a number line, I could draw this. Here's 0, here's negative 3, and here's positive 3. X can be any number as long as it's within 3 units of 0. So putting an upper bound on the absolute value like this is an upper bound because it says the absolute value has to come in under 3. So that's an upper bound. An upper bound is like a leash. It says we can't get any further than this from 0. The leash is 3 units long. We can't quite get to the end of the leash. We can get as close as we want to 3 or negative 3, but we can't go past them or to them. So that's how far our leash lets us go. Whereas if I put a lower bound on the absolute value, like x has a magnitude of 4 or bigger, let's say. X has a magnitude of 4 or bigger. So this is a lower bound on the absolute value. It could be 4 or any number bigger, but it can't be anything smaller. This is like the opposite. This is like a restraining order. 4 and negative 4. X could be negative 4 or anything smaller, like negative 5, negative 6. Those have magnitudes bigger than 4. 5, 6, 7, 10, a million, a billion. Those have magnitudes bigger than 4. So these are my solutions. X could be any of these numbers or any of those numbers. So an upper bound is like a leash, a lower bound is like a restraining order. Since the sign can flip when we multiply by negatives, we'll have to be very careful to be aware of both of those, leashes and restraining orders, as we go through this section. So let's try to solve an absolute value inequality. And I'll show you a couple of ways to solve this one. Thinking of absolute values as distance. Suppose that 2 times the absolute value, and remember this is a grouping symbol, so 6 minus m is all inside the grouping symbol. And let's say minus 3 is less than 7. So what I can do is get the grouping symbol by itself. Just like in equations, we're going to try to get that grouping symbol by itself. So I'll add 3 to each side, take care of the terms first and then the factors. And then I can divide both sides by 2. Whoops. And divide both sides by 2, so that's less than 5. No sign flip, because that's a positive. And no sign because you never sign flip when you're adding or subtracting. So now I see this is like a leash. There's a couple of ways to think of it. Here, let me show you 3 ways to finish the problem. I'm going to go with the leash to 0 method first, and then I'll talk about distance from 6 to m, and then I'll talk about pure syntax, because that's the way the book likes to do it, but meh. Meh. So the leash method, I'm saying 6 minus m is leashed to 0. It's less than 5 units away from 0. So here's 0, here's 5, here's -5. And these are all the places that the leash will let us live. So it's not this is the solution for m. 6 minus m lives on this interval. Actually, you know what? I'm not doing that. Okay. I realized this solution is going to include the pure syntax solution, so there's no reason not to explain the geometry. So the leash to 0 says this expression has to be within 5 units of 0, and it's 6 minus m. So what this is saying is we've got a lower bound and an upper bound. So down here, this is a lower bound, and it also had to satisfy an upper bound. It can't just satisfy one at a time. It has to satisfy both simultaneously. So this and is the operative word here. What I would say is 6 minus m, it's bigger than -5, and 6 minus m is less than +5. Lower bound and upper bound, because this leash works both ways. Of course, if I wanted, I could write this as a 3-part inequality. -5 is less than 6 minus m, which is also less than 5. It's between -5 and 5. Triple inequalities are pretty much made for this situation. So then, I only have 2 things to do. I can subtract 6 from all 3 sides. So I get -11 here, -m here, and -1 here. I subtracted the 6 from all 3 sides. Remember, it's all 3, not just 2. I'll write that. 6, 6, 6. All right, and now I have to get rid of this minus sign in front of the m. So I'm going to multiply all 3 sides by -1. I get 11, m, and 1. And because I multiplied by negative, I have to flip the signs. So my final answer is m is bigger than 1, so 1 gets a parenthesis, and it's less than 11, so 11 gets a parenthesis. So that's the regular solution. That's how you solve most of these. But in this problem, there's a special case we can use. Since this says absolute value of a difference, since there's subtraction inside, I can interpret this as m and 6 are less than 5 units apart. Because remember, the absolute value of a difference is distance between numbers. That's why, if you think back to the previous lecture, the absolute value of 2 minus 5 is the same as the absolute value of 5 minus 2. They're both 3, And that's because 2 and 5 are 3 units apart. So we could think of this as a leash, and the leash is telling us M and 6 are less than 5 units apart. M can get closer, but it can't get further away. So if you think of it that way, then you don't have to do most of the algebra I did on the left. This is a really easy solution. I say, here's 6. We've got a 5-unit leash, and M has to be on that leash. So 5 units down from 6 is 1. 5 units up from 6 is 11. Since this is a strict inequality, I put circles there. We can't quite get to the end of the leash. And M can be anywhere in between. It's like the post we drove into the ground is 6, and then we tied up the M to that post with a rope that was 5 units long. So if you think of that, well, then the interval is 1 to 11. So look at that, all geometry, no algebra. Now, the book has a solution that is all algebra and no geometry that proceeds from a purely syntactical understanding of absolute values. You can read it on your own time. I don't believe in it. I don't think you should have any business trying to solve these if you don't have at least some geometric intuition for what you're doing, because otherwise this is a horrible, horrible, awful, no good memorization game. Let's do another example. Heck, let's do a few more examples. These are tricky, and I want to make sure you get the full picture. So here's another one that proceeds like the previous. 3 times abs of 5 minus x. I got in the bad habit of pronouncing absolute value as abs, because that's how it looks in some programming language, just ABS. Specifically, that's how it looks on the programming language for my TI-89 calculator. I'm a pretty big nerd, you guys. Okay, so first I'm going to isolate the absolute value symbol. That's the same no matter what. So I'll get rid of the plus, 5 minus x, subtract 2 from each side. Now I have a 12. Divide both sides by 3. I'm going to switch up the order here. This says x is no more than 4 units away from 5. The distance between 5 and x is less than or equal to 4. So x is no more than 4 units away from 5. So here's 5, that's the post. We'll tie our 4-unit long leash to that post, so it could go up to 9 or down to 1. And we're putting closed circles there because there's a less than or equals to sign. This isn't a strict inequality. So my solution is x lives in the interval from 1 to 9. I know I'm throwing this in at a weird time, but by the way, this funny looking E I just drew means is an element of, which is a fancy way of saying it lives on that interval. So it's a weird looking E for the E in element. X is an element of this interval. I use it whenever I have a set and then I have a thing inside the set. So this says X has to be in the interval 1 to 9. Okay, that's just a side note. The main deal here is X was on a leash that was 4 units long, tied to the post driven into the ground at 5, and so it could go down to 1 or up to 9. Alternatively, we could say 5 minus x, and this is what you do if you don't have a minus sign here. We could say 5 minus x is 5 minus x is no more than 4 units away from 0. So here's 0, here's -4, here's +4, and that's the region right here where 5 minus x can live. So this way works too. And then I would say is 5 minus x, we have a lower bound of -4, and we have an upper bound of +4. And then what I need to do is subtract 5 from all 3 sides. And then divide all 3 sides by -1 to get rid of that minus sign on the x. When I do that, I divided by a negative, so the signs flip. And I get x is less than or equal to 9 and bigger than or equal to 1. So my solution set is 1, 9. Now you might be asking yourself, why does he bother teaching us this way if this way is so much quicker and cleaner? The answer is, if I had an equation something like, let's say the absolute value of 3x plus 4 minus 1, and how about times 3 is greater than or equal to, no. Let's keep this the same as the others, less than or equal to 8. What if I had this, right? So to get this by itself, I add 1 to each side. Now, some of you will be tempted here to add 4 to each side as well, or subtract 4 from each side. Remember, that's illegal because the 4 is stuck inside the grouping symbol. So the only way to touch the 3x plus 4 expression is to dissolve the grouping symbol, and we have to do that by interpreting it as a leash or a restraining order. So now I can divide both sides by 3. But now see, I don't have a difference inside here, so I'd be hard-pressed to come up with a way to interpret this as a leash between 3x and 4, because this is a plus and not a minus. That distance really works better with minus. There's ways to do it, but they're probably more confusing than they are enlightening, so I'm not going to get into those. Now let's just go on from there. What am I going to do here? Oh, right. So 3x plus 4 has to be no more than 3 units away from 0. So it has to live in this range. So the only way you can do that is if it's bounded from below by -3 and bounded from above by +3. So then I subtract 4 from all 3 sides. And I divide all 3 sides, Nathan, new sides. And then I divide all 3 sides by +3. So the signs don't flip here. X is between -7/3 and -1/3. And that's your inequality. Let's do 5 more. I know, right? No, let's do 5 more. We're going to see some weird special cases we can get into. So what if I said -4 is greater than or equal to -2 times the absolute value of 3x plus 1? First thing I have to do is divide by -2. So this is going to be a 2. This is going to be just 3x plus 1 in absolute value bars. But the sign flips. So this is a lower bound on the absolute value. The absolute value has to be bigger than 2. This is a restraining order on 3x plus 1. It cannot get within 2 units of the origin under any circumstances, or else it goes to jail. So here's -2, and here's +2. We have an equals bar. This isn't a strict inequality, so I can fill those in. And 3x plus 1 has to stay out of this neighborhood. So it can live up here on the right side of town, or it can live down here on the left side of town. But it can't live in the middle. So what I would say is 3x plus 1 has to be below or equal to -2, or it has 2 options here. It can live on the left or on the right, or 3x plus 1 can be bigger than or equal to +2. So then I subtract 1 from both sides and divide both sides by 3. Same thing on the right. I subtract 1 from both sides and then divide both sides by 3. So this is again an or. Either one works. It can be less than or equal to -1, or it can be bigger than or equal to 1/3. So here's -1, and we can go below that if we want. And here's +1/3, and we can go above that if we want, but we can't get in between. So our solution is, we can go from -infinity up to -1, or we can go from 1/3 up to infinity. Make sense? All right. Here's some goofy special cases. These are relatively simple equations because the point is to get some weirdness across. Suppose you told me that the absolute value of x plus 2 was less than -4. So this is a leash, it's a lower bound, but it's a really weird leash because it says we cannot be any more than -4 units away from 0. This leash is prescribing a negative distance. It's shorter than 0 units, and so it can't exist. There's no way to get any closer than on top of 0. If this were a 0, we'd be right on top of it, but this is closer than that. So there are no solutions. And that's because an absolute value can't be negative. To satisfy this, it would have to be like -4.01 or -5 or -10. That's impossible. Okay, what if instead I said the absolute value of x plus 5 is greater than or equal to -1? So this is a restraining order. We have to stay at least -1 units away. Well, that's closer than right on top of the thing. So look at it this way. If I plug in x is -5, then this whole thing is a 0. Its absolute value is 0. 0 is still at least as big as -1. Or if I plug in x is 10, 15 is bigger than -1. Or if I plug in x is -100, 95 is bigger than -1. There is no x I can plug in that'll violate the restraining order. So the solution is all real numbers. Any value of x will work because we were told we had to make the absolute value bigger than a negative number. Absolute value is always bigger than a negative number. How about another weird special case? Suppose I were told that x minus 5 has to be less than or equal to 0. So this is a leash, and this is the most restrictive leash possible that actually gives a solution. It says this absolute value, it can't be any bigger than 0. Now, it can't be negative. There's no way to get a negative, so really our only option is to make the absolute value equal to 0. This is saying the only way to get an absolute value 0 or less is if it's 0, because it can't be less. So this is telling us, actually, the absolute value of x minus 5, it has to be 0, because it can't be less. And so that means the only way for an absolute value to be 0 is if the expression is 0. And so that means x has to be 5. No other number works. If I plug in 5, I get 0 is less than or equal to 0. But if I plug in 6 or 4, I get a magnitude of 1, and that violates the leash. Let's do one more. Last one. What if I told you that the absolute value of x minus 6 has to be greater than 0? So this is a lower bound. It's like a restraining order, except it says you have to be more than 0 feet away from this thing. So you cannot be in the same place. This says the distance between x and 6. X and 6 can't be right on top of each other, but as long as there's any distance in between them, we're fine. So 5.9 works because there's a distance of 0.1 and that's bigger than 0. 6.1 works because there's a distance of 0.1 and that's bigger than 0. But 6 exactly doesn't work. So x is any number that's not 6. That's one way we could write it. There's another way we could write this, and this is going to feel really goofy, but we'll need it later. So here's 6. I'm not allowed to use 6, so I'm putting an open circle there. Any number bigger than 6 is fine, so I'm going to shade all of those in. Any number smaller than 6 is fine, so I'm going to shade all of those in. But 6 itself, no good. So my solution is -infinity up to 6, union 6 up to infinity. And I'm using parentheses there to say 6 is not included in either side. So anything bigger than 6, anything smaller than 6, just not 6 exactly. And there's our solutions.